Okay, so in this video we're going to be talking about Bohr's model of the atom, which is Unit 3, Syllabus 16. So for some context, Niels Bohr was a Danish physicist from 1885 to 1962, and he's most credited for the creation of a new atomic model, which is known as the Bohr model. One of the main ideas of this Bohr model is that it explained why atoms emitted light in fixed wavelengths. And something that kind of helps you remember him is that he received a Nobel Prize in Physics in 1922 due to his scientific contributions alongside this model. The main ideas of this model is that it represented a structure of the atom, much like many of the other models being formed at this time. It also described electrons as moving around the nucleus in fixed orbits and having a set amount of energy. Additionally, the Bohr model contains a positively charged small nucleus packed with different protons, surrounded by negative electrons moving around the nucleus in circular paths called orbits. Looking at the charges and the layout of the Bohr model, you can note that it's a circular model, unlike, again, some of the other models being formed at this time. And then here you can see the electrons being represented with negative charges, and the nucleus carrying a lot of the mass through positive proton charges. And then again, these circular paths are known as the electron orbits. Continuing on with some of the main ideas of the Bohr model, it was the first to address the connection between the wavelength of an element and its atomic structure, meaning that a wavelength can be determined to be higher or lower due to the number of protons in the nucleus of the atoms. Again, continuing on with this model, Bohr used Planck's equation, which is shown here, and applied that to Rutherford's model, which was known as the nuclear model of the atom, and although it was laid out kind of similarly, it did not have a circular path and the electrons were distributed differently. But anyways, he used Planck's and Rutherford's ideas to explain the general spectra of elements. Bohr also used this model to explain the energy of electrons must be quantized, which just simply means it has a certain amount of energy, depending on how far it is from the nucleus, or really what orbit it's in. This brings us to the idea of quantum numbers or orbitals. So quantum numbers are simply just the energy levels shown throughout this model, and they're represented with the letter n. So for example, energy level 1 is here shown as n equals 1, n equals 2, energy level 2, and so on. It's also important to consider that the certain orbits of electrons are represented here in these different energy levels, so that's how you explain where they are on the Bohr model. And you also need to consider this energy release here, which is important because it leads us to the idea of energy states. So there are two main types of energy states that follow along with the Bohr model. The first one being a ground state, which is simply defined as a state in which elements occupy their lowest energy levels, meaning their orbits are closest to the nucleus. And then secondly, you have an excited state, which is a state in which electrons occupy higher energy levels by absorbing energy, meaning their orbits are farther from the nucleus. Additionally, these excited states are typically more unstable than the ground states. And then looking back at this idea, your ground state would be on this quantum number 1, or n equals 1 energy level, and your excited states would be more out here as you move throughout the model. These states can be applied to the main idea coming from the Bohr model, which is known as Bohr's proposal. The first aspect of his proposal states that when a quantum, which is just simply a piece, of large enough energy is absorbed, an electron can jump from the ground state to some excited state. Secondly, his proposal states that after this, a quantum of energy is emitted by the electron when it falls back from the excited state to some lower state, which is often the ground state. It's also important to consider that the most amount of movement is equivalent to the most amount of energy changed when talking about the second aspect of his proposal. And this can be seen again going back to this image. You have these electrons moving from an excited state to a ground state, or just a less excited state. Ground state would be down here. And then you need to consider that the energy can be transferred and emitted and absorbed, and these electrons can move throughout the model. Moving on to the third idea of Bohr's proposal, he used Planck's equation, as stated before, to calculate frequencies from observed energies, and determined that that's equal to how far the electron falls. So simply, the further the electrons fall, the more energy released. And finally, the last aspect of this proposal is that Bohr observed the line spectrum, which is just simply the color given off by the element based on the model, which goes back to the idea of the spectra of elements that I talked about earlier. There's also certain limitations to this model that we have to consider. So for example, the ideas developed in Bohr's model really only pertain to hydrogen, which is an important aspect to consider. And additionally, it often doesn't fully account for all chemical behavior, as it really only applies to the idea of hydrogen. So moving into some images that can help you visualize different aspects of the Bohr model. This one here just represents some examples of the model throughout different elements, so like hydrogen, helium, lithium, it just keeps going throughout this, and you can consider the valence electrons here. This one shows the different energy levels throughout the different shells here, which is just another word for the orbits. This one explains the emission spectra and how wavelengths are used to calculate frequencies and the light of the Bohr model, or the light of the electrons. This one shows how to determine how many shells you need, depending on the valence electrons, and also it shows how you can write it with protons and neutrons in the center. And then this kind of represents a flowchart of all the aspects in the Bohr model that won't be completely covered in this class, but can kind of help contextualize that a little better. Moving into some applications of the Bohr model, the examples of some questions include how many valence electrons are in an aluminum atom. So first we have to consider this atom here, and it's asking about the valence electrons. So the valence electrons are going to be represented in this outermost shell, and it's a very simple problem. All you have to do is count the number of electrons. So this one just keeps you to recognize what shell valence electrons would be in, and it can help you if you don't have your periodic table on hand. So again, the answer is 3 valence electrons. Another question that may come up along with the Bohr model is how many electrons are in the n equals 1 shell of a silicon atom. So in order to observe this process, you have to answer the question by identifying the shell of the silicon atom. So you have to determine which one is the n equals 1 shell, and obviously it's represented by the ring closest to the nucleus. So after that, all we have to do is count the number of electrons, which are represented by these little dots, and after that you get 2 electrons in the n equals 1 shell. So for some practice on your own, you can work to draw Bohr models for really any atom that you're given. So if you want to pause this video, you just need to consider the amount of energy levels and valence electrons that go in this model, and also ensure you have the correct chemical formula in the center of it. So if you want to pause this is the correct answer. And also note, you don't have to include these n equal 1 labels or n equals 2. They're just kind of there to show you the different energy levels. And then another idea of practice, you draw the Bohr model for an argon atom. This answer shows it a little differently, as it poses the protons and neutrons within the nucleus rather than putting the chemical symbol in the middle. So you can again write it like that depending on the question it gives you. So pause it, but this is the correct answer.